We're probably going to be wandering for lunch. We'll try to close the front doors. So today's speaker is Hynek, comes to us from Europe, and he's going to talk about solid snakes.
Is this thing on? Hello? Hello? Okay. Everybody can hear me okay? Even in the back? Okay. You don't have to really hide back there, so if you can really come to the front. I don't mind if you play with your phones, and it gives a better atmosphere for us all. Just saying. So, thanks for coming, everyone. I'm here to talk about last year. More precisely about my last year. Because last year, after wrapping up PyCon US, I took advantage of being at the West Coast, because, as been mentioned, I'm from Europe, from Germany, and took a little road trip from San Francisco down to LA, up to Las Vegas, and back through the mountains. And when I was in San Francisco again, I decided it's too early to go back home, so I went to Hawaii. Now, this little tour plus PyCon took me 5 weeks. So I was more than 5 weeks away from work. And with every new photo I tweeted, more and more people kept asking me, how do I do it, and whether I actually still have a job. Now, it turns out I do have a job. And in that job, I'm responsible for more than 70 projects. And it turns also out that the answer to this question is longer than 140 characters. So it was here at the airport of Kauai, with a $7 plastic cup of beer. This talk was conceived. So I'm here to tell my story, or more like the things that fit into 45 minutes, which I think that are vital for my sleep. Often inspired by advice I've been giving in the past 12 months. So I will be touching on a lot of topics. And it will be ranging from DevOps to software engineering, so I hope there is something in there for everyone. And each topic, actually, is a talk by itself. And for that reason, there will be a link at the end of the talk with additional material for you to dive in and to study at your own leisure. Because I had to pick favorites for this talk, but it doesn't mean that you have to have an incomplete picture. So let's get going. And everything starts with attitude, as usual. You have to start value quality, which means that you will spend a significant time on non-features, which brings us to the next point, that it gets all down to incentives. Because everything seems to be high priority nowadays. If you ask your manager whether quality is a priority, they will probably say yes, although your web app crashes every hour. But if you do not have enough time to write tests, to instrument your infrastructure, it's about the same like a construction company which claims that safety is their top priority and lets their workers buy their own hard hats. So reliable systems do take time, and if your only performance metric is shipping new features, there's a conflict of interest there. However, there's hope, because it's not just about vacations. There's a solid business case to be made for reliable systems. Because the fewer urgent interruptions you have, the more you can work on important stuff. And the other way around, given enough unreliable systems, nothing new gets ever done again. There's no progress to be done, because everyone is busy fighting fires and keeping stuff running that's actually old. And that's exactly how I ended up with 70 projects, which I'm responsible for. Now, this takes long-term thinking, which is not always very common in our line of work. But yeah, there's no way around that. So let's get practical. And for my first point, I'm going to defer to authority, to Tony Hoare, which gave us Quicksort, which is a very accomplished gentleman in all things concurrent systems. Or if you prefer a Dutch sage, which makes totally sense at a Python conference, Edsger Dijkstra said basically the same. So the price of reliability is the pursuit of utmost simplicity. And at this point, you shouldn't be conflating simple and easy. Because an easy solution is almost never simple. And coming up with simple solution is everything but easy. Now, I find it the best to approach simplicity from the other side, from complexity. So what is complexity? It's basically the number of concepts you have to keep in mind when you're trying to reason about the behavior of a system, or when you're trying to reason about what happens if you change that system. And humans are naturally limited in how many things they can juggle, both literally and mentally. But if it becomes too much, you start dropping things. And if you start dropping things, you end up with normal accidents. This term has been coined by Charles Perrow in the wake of the 3 Mile Island incident. And they're called normal because they're considered inevitable in extremely complex, tightly coupled systems. Now, he didn't really think of your iPhone when he coined the term. But the fact is that we who work in computers are surrounded by complexity, by tightly coupled complexity. And let's imagine that your program is such a contraption. It's kind of impossible to reason about what happens if you play with this knob, or what happens if a part of the system breaks or starts misbehaving. Actually, it's pretty easy. Everything goes down. That's what happens, because the system is tightly coupled and the relationships are unclear and sprawling. Now, the irony here is that if you try to make this safer, you end up adding more complexity, which gives you more opportunity to fail. So the only realistic recourse in such case is to rewrite from scratch. Now, it's important to differentiate between two kinds of complexity. First of all, is essential one. That's the complexity that's inherent to the problem you're solving, like curing cancer or finding gravitational waves, whatever. The other one, so this is the good complexity. This is the one you get paid for. Then there's the accidental complexity, which is something you do to yourself. It's something that comes from wrong abstractions, cumbersome deployment procedures, or the usage of inadequate tools, like, for example, Python 2. I would drop my mic here, but I'm wired to it, so I guess I have to carry on. So everyone has accidental complexity they have to wrangle. But you should always ask yourself, when you're deep into a problem, what are you actually solving here? Is it something you should be solving, or is it something you did to yourself? Now, what is simple software? And this is going to be really quick, because this is not only a talk by itself, there's a whole conference by itself. But I do like the ravioli metaphor. And I've said that normal accidents come from tightly coupled systems. And ravioli is something that it's not coupled at all. And it basically says that a good design consists of many small objects, or even better, functions. Functions are awesome. That are self-contained. If you do ravioli properly, there's nothing leaking out, unless you overcook it. So, in other words, they should do as little as possible, and more importantly, they should know as little as possible about other parts of the system. This gives them a very clear interface, and it helps you to have simple relationships, because as many object-oriented programming mentors said before, dependencies will kill you. And by dependencies, I do not mean the things you install from PyPI. Donald Stuffed has your back, no problem. But it's the dependencies between objects. And especially bidirectional dependencies are pretty bad. And you should make as little assumptions between your objects as possible. And once you have achieved this place, it's very easy to test. Because you can instantiate small objects easily. It has little dependencies. You don't need a big load of fakes, mocks, or stubs, or whatever. Now, on the other hand, bad design. God objects. A God object is an object that knows too much and that does too much. And it applies just the opposite. So they're very hard to test because it's very hard to instantiate. Because you need all these extra objects to even do something. And the testing becomes less meaningful because if you need like 10 fakes to even test what it's doing, there's a chance that you are not really testing anything. Now, the problem is that God objects are pretty common in Python, because writing classes in Python is a tad tedious. I will come back to that later. Now, another complexity is mostly self-inflicted, is basing your design on subclassing. Or as Cory puts it, you will regret it. And I'm not gonna hate on subclassing per se. It's not a bad thing, but it's subject to misuse. And you should remember that subclassing has been made for specialization. It was not made for code sharing at all, and it was not made to model your APIs around it. And there's a bunch of rules around subclassing, like Liskov substitution principle, open-close principle, and if everybody would have following those rules, there would be no regret. But it is how it is. So you should always keep in mind that adding subclassing to architecture makes it more complex. It's easier to write, but you end up with namespace confusion and scattered logic. So if you want to understand the flow of your program, you have to traverse hierarchies, you have to understand the MRO. That's kind of tedious. So, but it's a trade-off, so it may be worth it. It may save you a lot of lines of code, but the thing, what I'm trying to say is that it's not where you start. Subclasses may or may not emerge from a good design for practical reasons, but you shouldn't start your project by just drawing hierarchies because that's what you've been taught. And another related concept are meta-classes, which are very powerful, but very overused. And I feel they're kind of like Python's monads, because nobody really understands them, and then every now and then someone reads about them and studies them, and then they write a blog post about how awesome they are. But in the end, again, you pay with complexity for syntactic sugar. So I would suggest that you leave them to David Beasley in his evil lair. He will do something really nice and depraved for us to enjoy, but you probably don't need them. Now, I've said that writing classes is tedious. So I agree, and that's why I wrote attrs. So how many of you have heard of attrs? Okay, it's getting better from year to year. So attrs, very quickly, will write class boilerplate for you. And I know those who did not lift their arms are probably restless to tell me about name tuple. And I do know about name tuples. But name tuples are not made as a class substitution. They are tuples with names. It's in the name. So the original idea around name tuples was if a function returns a tuple to attach names to it, so it's easier to use. And if you look at the standard library, it's full of that. A lot of functions return name tuples, and this is fine. But people started using them for classes, and they're just so you create a name tuple, you want to attach methods, so they subclass it, and if you want to change initialization, you have to write dunder new instead of dunder init, and this is no bueno. So attrs gives you a simple class. Just a regular class. It will write the boilerplate for you, attach it to the class, and it will leave you alone. And it has many goodies like validators, converters, default values, including factories, so it's really great. And now you may be asking, Hynek, is this a serious project you should use? And I'm so glad you asked. Yes, it is. I have stickers. So come to me and get your attrs stickers. And you really don't have to stand over there. Here's like everything empty. Just come in, I don't mind. Movement is good. So, with that, let's move on. Operational complexity, which is the complexity of running your infrastructure or parts of infrastructure. And I don't think it's controversial if I say that distributed systems are hard. Now let's look at a very simple distributed system, like this. I would say this is kind of best practice. You have a client, you have a CDN, which is not in your DC, you have an application which is in your DC. The application has a worker queue, it has a database, it has a Redis cache. Now the problem with this good design is that you already have a lot of single point of failures. And the sad thing is that there's more. It's not just the boxes. The links are points of failures too. And now you have 10 independent points of failures. And if you know something about probabilities, you will know that's not good. They basically are adding up. And the problem here is, of course, that network partitions are a thing. So a lot of people live in denial. And they just say that it's not a thing, it's rare, it doesn't happen, until it happens to them. And then they change their mind, but then it's pretty late. So I would like to cite a paper from Google, and when they set up a new cluster In the first year, they see 3 router failures, 8 network maintenances, 12 router reloads, and I'm running out of fingers, and 40 to 80 machines see a 50% packet loss. So they are rare, but they happen. And if you happen to run at scale, rare events are common. So think twice before adding new red boxes and new red links, because all of them add new exciting ways for failure. And with that in mind, let's talk about microservices. Microservices are about splitting up your application into small web services, which means you get a lot more red boxes and a lot more red arrows. And which means that you go from a big monolith, which has some bad properties, which we all know, and that are annoying, but you end with something like this, a highly distributed system. And you may or may not be equipped well to deal with it, because now you have new decisions. Are you going to have a tangled mess like this, or are you going to use a message bus? Which message bus? How do you decide? And you have new problems, which you didn't have before. Service discovery, aggregate logging, tracing. You should not even think about microservices without having a tracing infrastructure in place. Otherwise, it's impossible to debug it. And other fallacies of distributed systems which are there to bite you. Now, what you really want and what you really need are boundaries. So you need to define and adhere to APIs and boundaries between your modules and your packages. You don't need a network between your classes to have a clear boundary. And that allows you to have separate teams working on separate parts. You have clear interfaces, everything is good. And once you've established boundaries, it's also very easy to migrate to microservices eventually if you need to, because there are good reasons for microservices. For example, scaling out, or heterogeneous environments. That's me. I have quite a bit of small services because I need to interface with PHP and Perl. So that's a thing. And also, finally, I need to say that complexity is not the devil, it's a reality. And it's a price you pay for getting stuff done. So you should consider it a currency. And the important thing about a currency is that the budget depends on you. It depends on what you can afford. So the price can be super high. My favorite example is Kubernetes. Kubernetes is super cool, and it's very easy to set up. I've set up a Kubernetes cluster like 5 times, but it's super hard to keep running and to keep it running well if you do not have specific staff that is schooled with that. And you also don't have to stand there. There's a lot of space here. Just walk in, no problem. Now, because once it's running, it's fine. But what do you do when it starts screeching? Do you understand etcd, Flannel, Docker, Prometheus? They're all pretty complex by themselves. But if you can afford it, and if you have the knowledge and the resources, awesome, use it. But if you take technology which you do not understand, which you do not master, put it into prod because it's cool, you can start reading Dante about your future. So what I'm saying is you cannot run it on the side. You just can't. You can start it on the side, but eventually the 7 circles of hell are waiting for you. Now, speaking of stupidity, this is of course an hyperbole. Things are only stupid in hindsight, but people act stupid sometimes. For example, if they're sleep deprived because the baby cried all night, or because they're at a busy airport, they want to board a plane and they will try to deploy really quick something. Or they're hustling really hard to satisfy some rich VC in San Francisco. There are many reasons to act stupid. But I would like to quote John Allspaw, the CTO of Etsy, and he doesn't believe in human error, and neither do I. I believe that if a human causes an outage, it's usually because a system failed them. It's very rare that people do something stupid out of malice or ignorance. So I'm sure all of you remember the S3 failure a few months ago, which took down half of the internet. If you read the post-mortem, which you should, it's super interesting, you will see that the outage was caused by a human using a tool in the wrong way. However, the post-mortem puts emphasis on fixing the tool, not on firing an employee or pointing fingers. A system failed that employee. Now, when building tools and APIs, you should always assume that the operator is drugged from the dentist, consoling a crying baby, or hasn't slept properly for a few days because they just came from Central Europe to the Pacific Northwest and are jet-lagged AF. So, if it takes one click or one API call to lose all your data, someone will make that click or that API call. Maybe they just try to clean their phone screen or something, but someone will eventually click. And then it's your fault, because if you add sharp edges to your software, it's your fault if people hurt themselves or you. You don't get to complain. And it's kind of similar to products for handicapped people, because it turned out that accessible products are better for everyone. And that's the same with tools and APIs. Now, an intersection of sharp edges and complexity is, or are, class instances that end up in an illegal state, which means the attributes have values that make further work of that class impossible. And my favorite solution to this problem is to make this illegal state unrepresentable, which means that your objects are always in a valid state. So you do not have to keep track of your state, which gives you a lot less complexity. And to get there, you basically have to do just two things. First, your objects have to be valid after initialization. And secondly, you have to prevent them to mutate into something illegal. The first part is pretty easy. Don't do APIs like this. If you allow for partial initialization, you end up with a lot of if statements in your classes, because you have to always check, am I connected? Am I configured? And Sandy Metz, object-oriented programming mentor in the Ruby community, which I admire greatly, once said that if statements in classes always get worse. They're kind of a code smell. So if you end up with a lot of complex if statements in your classes, it's very likely that you got some abstraction wrong. And my personal philosophy is that initializers should only return valid objects, but they should be super simple. So it's okay if they validate data, but they should not derive data, should not create data. And for God's sake, they should not do any I/O. So what I do are class method factories. They give you a really nice API, connection.connect. I know what it's doing. It connects to a host name with TLS true and returns a connection. And I'm at this point that I consider dunder init methods kind of private APIs and abstract away all my internal states and data structures like sockets or something like that. So in this case, the initializer of connection could take a socket object. This allows you to have I/O in a constructor, like in a factory. You can use async I/O here. You can do async await, which you cannot do with dunder init. And it's highly testable, because you can instantiate connections with a fake socket object, and you're done. It works. Another popular approach is the build-up pattern, which means you have a separate object to create to configure it, and then build it at the end. So connect would just fail at the end if the information is not valid. So you, again, get only valid connections. Now, how to prevent mutation to illegal? So you can use properties in state machines, and I've done this before, but it's a bit fiddly. I kind of prefer it, if you can pull it off, to prevent mutation at all, which is kind of the functional programming approach, which means that you don't give your users APIs to modify your objects, but you give them APIs to create a new object based on this object. And this reduces your problem to problem number one, that you only allow the creation of valid objects. And this is especially appealing if you have a method called recalculate, rebuild, or validate on your classes, because you're obviously doing some global thing and need to derive your data anew, and then you can just create a new object and you'll be fine. So your abstractions can be perfect, but the data that's coming in is not perfect. It will not be perfect. And it doesn't matter if it's malicious or a mistake. You should always be careful what you let in. And in that point, I fundamentally disagree with Postel's law. I think you should be conservative both at sending and at receiving. And this, by the way, was neither malicious nor a mistake. It was delicious, and the only thing I liked about San Francisco. The link to the taqueria is in the talk page. So invalid data, I like to think about it as a time bomb, because it's a thing like an invalid date string. So it's a string with a date inside, but you do not really know, is it valid? And such a thing wanders through all your system, and the deeper it gets, the more damage can it do. And the sooner you catch it, the better you can react to it. So for example, a web view can give you a reasonable error if you pass it an invalid date. An ORM will probably just explode with a 500, and the user is confused what went wrong. So other edges are aforementioned under init, command line parsing, just do it at the edges. But I think validation is not enough. I feel that, I believe that you should get your data as soon as possible into a simple canonical form. Because a form that the rest of the system can just rely on and doesn't have to make assumptions about whether it's something valid and in what form it is. So your business logic shouldn't even know what JSON is. So you should just pass it a dictionary. Or maybe if you do know the structure of your data, you should pass it a class. Because I really think that dictionaries only really make sense if you ever iterate on the keys. If you know what's in the dictionary, make it a class. It's easier to type, and it gives you some properties that it's harder to make mistakes, and those mistakes are more likely to be caught by the interpreter. Or passing around strings in general, it's not always a good idea. So, because it often makes a function a parser, and parsers are very dangerous. So just try to use first-class objects, enums, things like that. It will make everything much more fault-tolerant. There are a lot more time bombs I know about, but I don't have time. Talk page. Now, the problem is everything I told you is true, and it will help you to have more reliable systems. But in the end, failure is inevitable. Something will fail. And if you work in computers, failures are part of your life, whether you like it or not. So in practice, your reliability will land on a spectrum that goes somewhere from Twitter in 2007, which had 98% uptime, which is 6 days off, and NASA in 1969, which landed on a goddamn moon, despite a human error on descent. But the software was robust enough to compensate for a human error in 1969. Now, the problem with NASA's reliability is that you need an actual genius to write the software, a genius that will just, on the side, invent software engineering. So unless you have Miss Hamilton on your staff, you may have to scale down your expectations. If you do, I would like to apply for an internship. I take up a lot of space, but I eat very little. So, okay, so failure is inevitable. So what you can do, you can minimize risks, you can prepare for it, and then you have to deal with it. And I'm just going to give away my talk here. A long undisturbed vacation is the result of good failure containment and solid recovery. And let's shift gears a little bit here and talk about that. Now, you've embraced that failure will happen, so you need to actively expect it. So how do you actively expect something? You monitor it. So if you run a service, for example, you need to look at it if it's really doing what you're doing, what it's supposed to do, because for all you know, it's down, unless you check for it. You need to check for outages, you need to instrument your systems, and you need solid error reporting. This is true for both like long-running services, but also for applications, for scripts, for everything. Because silent failures are the worst. Now, I've talked about these things in the past 2 years. My taste did not change. I still love Prometheus for instrumentation and monitoring, and I still love Sentry for error reporting. Both are open source, so there's no reason to not use them. Now, in your code, if you expect failure, there are basically two classes of things that can happen. The local errors are easy. An exception is raised, and you deal with it. Remotely, you're actually lucky if it fails right away, like a connection refused or a 500 from a web service. What's much worse, and what happens very often, is that just nothing happens. And that means that whatever you do remotely, put a timeout on it. One missing timeout in a database driver was enough to ground an entire American airline. So nobody's immune from that. Timeouts are one of the most important things in distributed systems. Now, if you start getting timeouts, what do you really do in your application? Do you carry on? That gives you a lot of slow and completely useless requests. And if your system is suffering from overload, it will also make things worse. So for that reason, there's a super useful circuit breaker pattern, which I'm just going to quickly introduce you to because it's so simple and so useful. Now, it's kind of a local proxy between you and the remote system. And in its normal state, it's closed, like a drawbridge. The requests are flowing out, results coming back in. Now, if something happens, like a timeout or an error or something, it will change from closed to open. Again, drawbridge. You usually don't do it on the first error because transient errors are pretty common in distributed systems, but after 2 or 3 timeouts, you should really take some consequences. Now it's open, and the circuit breaker starts ignoring the remote API, and it's serving errors to the client immediately. So you get very fast turnaround times, and you leave the remote API alone. Now, after a certain time, you send out a probe. So it's one lucky request that will send out to the remote API to check if it's still broken. If it succeeds, bridge is being closed again, everything is flowing. If not, it stays open and we will check on it later. This is an example for a very simple but very effective technique, so you should add it to your tool chest. So, before I say that adding more components to your systems is bad, and it's true. But if it's the same component, and if you put a component that's much more reliable than your component, like, for example, HA proxy, which is, and I don't say this lightly, very good software, it might actually improve the reliability of your systems. And there's this saying in the American military that 2 is 1 and 1 is none, and that's exactly how you should be thinking. So you should have 2 of everything, and the really important things you should have 3 of, so you never get into the situation that you have only 2, which is 1 and which is none. So this principle made the internet almost unbreakable, except that too many people are using the same DNS provider, and too many people are using the same storage service in the same region. And it works at any level. In a network, you want multiple uplinks, you want multiple routers. Server hardware, you want more than one server, obviously. Data centers, ideally, if you're big enough, or availability zones, if you're in the cloud. And this is, of course, also true for backups. For example, let me tell you that if this is enough to lose all your data, you do not have backups. And also, if you do not test your backups, you also do not have backups. And if you do not believe me, you should talk to the lovely people at GitLab. They will tell you about testing backups. So, if you want to be dispensable, you can be a knowledge silo. So, if people ask you something regularly, write it down. If you have some regular tasks, some standard procedures that needs to be done, write them down. And if something needs to be done in a case of emergency, write it down. Don't rely on remembering things, because it's a very dangerous fallacy, and the safety of the aviation industry basically relies on the fact that there's a checklist for everything. And that's the same thing you should be doing. Because if there's chaos and an emergency, you want to have contingency plans. And that can also be about communication, because that's something a lot of people like to forget. But you should tell your social media team that your database server is on fire, so they don't just lie to your customers that everything is fine. Okay, finally, how do you deal with failure? What do you do in your app if your database is gone, if a web service starts returning invalid responses, if you're getting timeouts? So the first rule is don't make it any worse. Because in the worst case, you're getting a cascading failure, which means that everything just melts, and you take down services that are completely unrelated to the one that is melting. But if you're not careful, you take down everything. And let's talk about something very simple with a very big impact, and it's retries. Retries are essential in a distributed system. Transient failures are everywhere, but they're also super dangerous. Because if you use them loosely on yourself, you can DOS yourself. If you use them loosely on a third party, you may just get blacklisted, and then you have a lot of explaining to do, which is bad for business. So you have to back off if you want to retry. But how long do you back off? If you ran into some deployment thingy, 1 second is fine, it's back. If a system is overloaded and you're waiting for a backend to come up, maybe 1 minute, give or take. If a switch is broken or something crucial hardware-wise, it can take hours until some poor sod makes it into the DC and fixes the hardware. Maybe you should just check every 5 minutes if the problem still persists. Now, how long do you back off? The answer is all of them. You start with a very short period, and then you raise it exponentially. Now, this is good, but not good enough. Because if all services do this, you still have a lot of load at the same moment when they retry. And that's why you still have to add a jitter. A jitter is just a random number that you add to your computed backoff, and it will space out the retries so your server doesn't melt immediately after the computed backoff. Now, this is kind of intuitive, but let's look at it closer. So let's say, you have a policy of 3 retries. And let's assume the backend is your responsibility, and let's assume you read the orange news page. So what do? You do microservices. So at this point, if something goes wrong in the backend, you get 3 times 3, which is 9 retries. But this is not even close to microservices. Let's go once further. And you're DOSing yourself again. This is called a combinatorial retry explosion, and you're hitting C with 27 retries for 1 retry in the front end. Now imagine that if C was flaky because it was overloaded. Now it's toast. Now there's no chance that it ever will recover. And a simple solution, which I take, is that you retry only at the top, which requires you to know where your top is, which may or may not be true, depending on your size. So it can get a lot more complicated. Things like per-request retry budgets are a thing, which means that you have to pass a state through your requests. And this is also a nice example for a complexity that you get through microservices that you would not have if you just have a nice fat monolith. And again, there's much more to be said. Back pressure, you should be able to signal to your other systems that you are kind of overloaded. Unbounded queues, it's very simple, do not have them. Do not have a queue that is not limited in size. It's mathematically proven that they are terrible. Don't have them. Again, no time, linked at the end. So, next one. You want insight into failures. They happen, you want to know what's going on, so you can react meaningfully. What happened? Why did it happen? And nothing is worse than a silently failing backup script. I'm sure everyone had it at some point. So you should instrument or add some error reporting to your backup scripts in any case. So maybe Sentry or just send an email. It's enough. Just make sure that your failures are not silent. And this is true in your code too. If you write code like this, especially in public libraries, I have a lot of opinions. This is really not good. How do you debug this? How do you even find what's going wrong? And the same goes, by the way, for, I like to call them vanity exceptions from your library. It's nice that the exception has a nice name, but still the error details are lost. This is no way better than the one before. So what to do? Exception chaining. If you do this, the original exception is attached to your new exception, and you can introspect what went wrong. If you're using Python 2, I do feel sorry for you, but there is also a race_from in 6, the compatibility library. So there are ways to do this in any version. Now, I would like to just say my personal opinion that if you write a library and an exception happens which you do not know what to do with, just let it go. Let it fly. Let it soar. Because your users will know what to do with it. So if you do not know it, just let it through. That's the nice thing about exceptions. So This one is a bit counterintuition, but if your application is unfit for work, for example, like, your connection pool is invalid because someone restarted the server, the database server, you could start adding complexity to your application. Like, in one part, you're trying to reconnect to the database, but you have to make sure that you try it only in one place. You have to kind of handle the intermediate requests, or you should just add one line to your code. And this is a very good solution more often than not. And in this case, if you use sys.exit, your @exit handlers are called too before the exit actually happens, so you can clean up after yourself. But it saves you a lot of code. And this is not something I've invented. It's called crash-only software. There are scientific papers on it. And there's a bit more nuance to it too. So things like micro-reboots, which are, like, unfortunately a bit harder in Python. But it's a thing. And it's it's better than you may think in the first reaction. Now, what I'm saying is fail fast and fail loudly. A crash is much better than a hang. A quick 500 is also much better than a hang. I mean, what do you prefer? If you click on a link, I prefer to have a 500 after 30 seconds and not a browser error after 3 minutes while wondering what's going on. And depending on your audience, it might be worth it to show them an informative stack trace instead of just telling them that an error happened. And Redis, the key value database, takes it to the new level. Because if it crashes, it will show you a stack trace, and it will run a very quick memory test, because a lot of crashes come from bad memory. So they can tell the users right away that their memory is broken and they should not report this bug. Now, once you've done all of this, you need to focus on recovery. Otherwise, it does not work. And this is where the MTTR reigns supreme. The MTTR is the mean time to recovery. So because if you've accepted that failures happen, and maybe even start writing crash-only software, it becomes much less important whether something goes down, and much more important that it comes up again, fast. And that's why no humans can be allowed when you're restoring your service. In other words, I should be able to pull the plug of in your DC, plug it back in, and your infrastructure has to come up on its own. And to make this happen, there's one prerequisite in your application. You have to have zero expectations about what is already present while you are starting up. What I'm saying, if I take your production container, run it on my notebook, it should do something meaningful. It should tell me that it cannot connect to its database, wait a back off, and try it again. You can also crash, but then you have to make sure that you can do your backoffs outside of your application. So I just do a loop. So, wrapping up, what is the secret to a long, undisturbed vacation? Apparently, $9 Mai Tais in a plastic cup? Seriously, what's wrong with plastic cups in this country? I don't understand it. But other than that, build fault-tolerant systems that recover autonomously, and then switch off your phone. This is the promised link. The QR code will bring you there. Follow me on Twitter, buy domains from Vario Media if you speak German. I would like to announce there will be an open space about reliability. I will force some smart people to come there, so it will be worth coming there. Just watch the board, and thank you very much.
Thank you very much, Hendrik. So we're not going to have questions. He's going to take them in his open space later on. So we'll move on to the next speaker. Thanks, Hendrik.
Just about vacations. There's a solid business case to be made for reliable systems. Because the fewer urgent interruptions you have, the more you can work on important stuff. And the other way around, given enough unreliable systems, nothing new gets ever done again. There's no progress to be done because everyone is busy fighting fires and keeping stuff running that's actually old. And that's exactly how I ended up with 70 projects, which I'm responsible for. Now, this takes long-term thinking, which is not always very common in our line of work. But yeah, there's no way around that. So let's get practical. And for my first point, I'm going to defer to authority, to Tony Hoare, which gave us Quicksort, which is a very accomplished gentleman. $7 plastic cup of beer. This talk was conceived. So I'm here to tell my story, or more like the things that fit into 45 minutes, which I think that are vital for my sleep. Often inspired by advice I've been giving in the past 12 months. So I will be touching on a lot of topics. And it will be ranging from DevOps to software engineering, so I hope there is something in there for everyone. And each topic, actually, is a talk by itself. And for that reason, there will be a link at the end of the talk with additional material for you to dive in and to study at your own leisure. Because I had to pick favorites for this talk, but it doesn't mean that you have to have an incomplete picture. So let's get going. And everything starts, as been mentioned, I'm from Europe, from Germany, and took us a little road trip from San Francisco down to LA, up to Las Vegas, and back through the mountains. And when I was in San Francisco again, I decided it's too early to go back home, so I went to Hawaii. Now, this little tour plus PyCon took me 5 weeks. So I was more than 5 weeks away from work. And with every new photo I tweeted, more and more people kept asking me, how do I do it, and whether I actually still have a job. Now, it turns out I do have a job. And in that job, I'm responsible for more than 70 projects. And it turns also out that the answer to this question is longer than 140 characters. So it was here at the airport of Kauai, where it starts with attitude, as usual. You have to start value quality, which means that you will spend a significant time on non-features, which brings us to the next point, that it gets all down to incentives. Because everything seems to be high priority nowadays. If you ask your manager whether quality is a priority, they will probably say yes, although your web app crashes every hour. But if you do not have enough time to write tests, to instrument your infrastructure, it's about the same like a construction company which claims that safety is their top priority and lets their workers buy their own hard hats. So reliable systems do take time, and if your only performance metric is shipping new features, there's a conflict of interest there. However, there's hope, because it's not...
We're probably going to be wandering for lunch. We'll try to close the front doors. So today's speaker is Hynek, comes to us from Europe, and he's going to talk about solid snakes.
Is this thing on? Hello? Hello? Ah, okay. Everybody can hear me okay? Even in the back? Okay. You don't have to really hide back there, so if you can really come to the front. I don't mind if you play with your phones, and it gives a better atmosphere for us all. Just saying. So, thanks for coming, everyone. I'm here to talk about last year. More precisely about my last year. Because last year, after wrapping up PyCon US, I took advantage of being at the West Coast, because